error library know how to brute force keys in software, just abstract everything away into the library so that, you know, if you've got an FPGA hooked up, great. Everything that I've ever written will now run hardware accelerated, including JC aircrack. If you don't have an FPGA, that's cool. I'll do it in software. And if you've got some other hardware that could do this later, like a GPU, you know, you can reprogram those if you know what you're doing. Maybe it could target that later. And if anybody's ever seen OSX's core image stuff, this is kind of inspired by that, because that's a really cool design. It sort of has the same look to it. So basically, how the Pico client works is gets a start key, a stop key, a key size, and a hopeful PRGA, which is a pseudo-random generator output, I think. Anyway, it sends it off to the FPGA, and then it says, okay, FPGA, go. Seems that's how these all work. You send the FPGA some stuff and tell it go, because it's just dying to do something. So, and then the client, all it does is, while the Pico chip is busy, update the display. It's not using any CPU cycles there. You know, it's like, you done? I got nothing to do. So what you could do with those CPU cycles is run another copy of the, you know, software-based client and get, you know, more bang for your buck out of your CPU. So that's all of Airbase. That's a lot of code. In fact, I checked yesterday, and I have 20,000 lines of wireless code. They all compiled on x86 OS X without changing anything except one line. So that was cool. Anyway, here's back to Dave's stuff.
Thanks.
No problem.
Thanks a lot, Johnny.
Whatever.
So I'm going to talk a little bit about the specifics on how the FPGA core works that we use to accelerate all the RC4 stuff. Right now, you can either use an image that I made that has 32 RC4 cores or 48. And all these, I made all of them so they're really lightweight, really tiny, so you can just fit a ton of them on the FPGA. And yeah, I'll go into the performance numbers later, but it basically wraps around a block RAM on the FPGA. So the block RAM is used as an S-box, and here's just a really tiny state machine that just handles all of the sort of RC4 stuff around it. And it'll just try every key with, you know, from the start to the end and spit out PRGA and just compare it, and it's a pretty simple brute force algorithm. So if you look at RC4 normally, it's a really simple algorithm. Basically, you just have your initialization where you create this permutation between like 0 and 255. So it's just assigning like each index into the S array to whatever, you know, the index is. And then it kind of goes through, and based on the key, it just starts mix and matching, like swapping different values inside the S box. And then eventually, it kind of does some more swap stuff and outputs a byte during every cycle in the PRGA step. And then that's your basically random output based on your key. So if you put in a key, you'll always get this random stream of bytes that can continue on, you know, until infinity. But yeah, basically that's how RC4 works. It's just basically a PRGA algorithm. So right now, the computer just sends a start and a stop, and whatever the expected PRGA is, and you get the PRGA by basically grabbing a packet, and you know what the first like 5 to 8 bytes or whatever the packet is. So you XOR that with that, and then that should be the bytes that come straight out of RC4, if that makes sense, because those get XORed onto the data, you know, the actual payload for the packet. And so with that PRGA, you're just looking for a key that will match up with the PRGA that you're getting. And so right now, the computer feeds this over to the RC4 keygen thing over here, and then it starts farming out keys. It says, okay, RC4 core over there, you know, try key 0, and then you over here try key 1, and you over here try key 2. And then it sends back a PRGA, so one of them says like, hey, yeah, it's actually woot, it's actually going to be some hex values or something, but just for fun. It actually
spend a lot of time on this, because this is our good slide technique right here.
What's that?
This is our good slide technique right here.
Exactly, yeah. Yeah, it's all metaphorical to some cool hex values. So then this one says arg, this one says Hammy's my hero, and then none of them match the bling over here. So
no
you
bling.
keep on going, you know, farm out. Okay, you try key 3, key 4, key 5, and then they go back, and then it's like, oh wait, there's bling right there. So I guess that the key must be 4 because the PRGA is bling. So then it, you know, goes like, okay, the key is actually 4, and then it's all cracked. Some cool optimizations that you can do with RC4 and hardware is this whole initialization step. Normally you deal with a block RAM where basically you have an address, data, you know, and then like a write enable or something like that. And basically every cycle you feed in, okay, address 0, you know, write 0, and yeah, there's a write enable enabled, so just write a 0 into there, and then, you know, write a 1, and then a 2. And that takes 256 cycles to go through all of that. So the rest of the algorithm here takes maybe, you know, 500 cycles normally. And so adding on another 256 just takes forever. One of the first optimizations I thought of for initializing kind of in parallel while the thing's going on is to basically have 2 block RAMs where you kind of have your master block RAM over here, and then you have 2 of them, and in the first stage, it just fills like, you know, block RAM A, and then this RC4 core over here starts using the A block RAM, and then it starts, you know, swapping values around and writing to it and stuff. And while it's doing that, then it's initializing B, and then when it goes on to cracking the next key, then it switches over to B, which is already all initialized and good, and so then it messes with that one while A is getting filled. So it just swaps back and forth. And so I thought that was a pretty good design at first, but it turns out there's actually a better way to do it. This better way is basically you're addressing it as an 8-bit block RAM, but what if you make it a 16-bit? And so for example, like if you read from address 2, you only look at the bottom 8 bits. If you read from address, you know, 54 or 57 or whatever, you only look at the bottom 8 bits. And in the KSA, you're writing to every single value in there because you're going through and swapping, you know, like, okay, 0 gets swapped with this, 1 gets swapped with this, you know, 2 gets swapped with this. And so you're actually writing to every single value in the whole thing. And so why not, when you're writing, just set like the top 8 bits of the 16 bits to whatever your address is. And so essentially like the top, you know, 8 bits in the whole block RAM will be initialized once you're done just by the pure property of the KSA because it writes to everything. And so, so yeah, you'll end up with like at address 0, there's 0073, address 1, 019B. And then once you're done with this whole, you know, for your first one, you just swap over, and now you're using the top half of the 8 bits instead of the bottom half. And so it's kind of cool. With this, you only have to use 1 block RAM instead of 2. And it's a lot more fast because all your logic can be just right around the block RAM and stay really close to it. So that's one of my optimizations. If you can think of a cooler, better one, just let me know. So yeah, so then everything's happy here. I'm going to go on to a demo. Oh, actually, maybe we should have a slight intermission and throw on a movie.
Yeah, you know, it's the last talk of the day.
Yeah. Might as well.
We should explain this particular, you know, slide though before we cut into this. So, well, you're good at this, so I'll let you.
Oh, okay.
You want to do the blank plus blank equals blank?
Oh, yeah. So this is JC WebCrackD over here, and this is one of our Pico cards. That's a quarter right there, so it's pretty small.
This is essentially this card.
Yeah, and this is Neo like shooting up some shit in the Matrix. And you may ask yourself, what do all these things have in common? And you'll find out soon enough, but before that, we just want to take a quick break and...
So we're talking about the Matrix. We're also going to be talking about performance. And with that in mind, yeah, we have to mic it. Get a little above this. We're going to try and mic this ourselves, so hold on a second. Move a little up here. Okay. Can you hear it?
What did you think about that fighting and stuff in the Matrix? Do you think that it was, you know, they like ripped those techniques off of you, or what?
You have got to be kidding me. That fighting couldn't be any further away from ninja fighting if it were a brick trying to beat Jupiter. First of all, the actors are already fighting at a ridiculously slow level. If you took the regular footage of them fighting regular speed and then played that at 400 times faster, that would be about half ninja speed. Look, just get ninjas in there who can actually do it that fast. Unfortunately, it's difficult to capture us on film, which is at about 24 frames per second, and the human eye processes at about 72 frames per second, and ninjas can move at roughly 84,000 frames per second. On a bad day, it might get down to around 60,000 frames per second. We're really flipping fast, and we fight that fast. So, like, us watching The Matrix is like is like watching a retarded bear in the circus. It's painful and it's annoying, but it's just frustrating because you wish there was something you could do, but you don't really want to watch it. Nobody really wants to see that. You know, they're on a little bike, and you're just like, take them away from all of this. You know, I put in an order form to try and kill everybody associated with the Matrix. Hopefully that'll come down the pipe someday soon, because I would like to give those Wachowski brothers a couple fists in the head. V for vendetta. Well, I've got a vendetta against the Wachowski brothers.
So that's our interlude. Okay.
So the metaphor out of that whole video is that like your server cluster is you know, those dudes in the Matrix, and this is kind of the ninja stuff here. So.
All right. You want to get set up and tell me when you're ready?
All right. So on these cards, we've got different images loaded onto this little flash chip that we have on there, and we can swap them out on the fly. So before I was running the image for Cow Patty, and I just swapped it over to use the stuff for the Pico web crack stuff, and you can have like up to about like, I don't know, 60 different images on there, and you can swap them out, and it takes like, you know, maybe about 1 or 2 milliseconds to swap images. So that's the cool thing about reconfigurable computing. Let me start up the demo here.
The other cool thing about reconfigurable computing is reconfiguring the monitors.
So I made another screen script that basically fires up the JC web crack daemon, and then fires up, oh, why don't you switch it over?
No, here, yeah, I got it.
Okay.
Give me the other one.
Oh, yeah. This should take a little while to crack, so.
All right, magic hour. Yay! All right, so come on down, come on down.
Oh,
we can describe it from here.
Oh, okay. All right. So yeah, this is running the JC WebCrack client. This is actually one out of 16 instances that are running right now, and this particular instance is doing about 3 million keys per second, and so that times 16 is pretty fast. And it should go along and eventually find the key. I think this is the session that'll actually find it, and Johnny added in a cool animation once it finds it, so we'll wait for that. Let's see. Yeah, so each card gets around 6 million keys per second, and in the 48 core version, then you can get about like 9 million keys per second. On
almost
normal
10
computer,
million.
What's that?
Almost 10 million.
Almost 10 million, yeah, yeah.
Basically 10 million.
Yeah, so on my laptop, my huge freaking like P4 3.6 gigahertz laptop, I get around maybe 1/3 of a million, like about 300,000. So it's pretty quick. It should be coming up soon here, I think.
Yeah, bear with us in our supercomputing.
There we go.
Hooray!
There we go. So that's the demo. Yeah, ask Johnny later about how he did the matrix effects. So yeah, those are all the performance numbers here. But yeah, we can brute force, one of these systems can brute force a 40-bit key in around like, I think 13 minutes or something like that, or pretty quick. Yeah, there you go. Yeah, sure.